In this video, we're going to learn even more about definite integrals. We're going to learn something called the average value of a function. We're going to learn how to do substitution with definite integrals instead of indefinite integrals. And we're going to learn how to do more complicated fundamental theorem of calculus problems. So let's just get started with the average value. The average value of a function f on the interval AB is given by 1 over b minus a times the definite integral from a to b of f of x dx. Now this might look a little familiar to you because we just learned about something called the mean value theorem for integrals, and this was one side of the mean value theorem for integrals. So yes, our mean value theorem is saying that there is some value c in between a and b such that f of c is equal to this integral, the average value of the function. So let's do a practice problem finding the average value of a function on an interval. So find the average value of the function f of x equals 1 plus x squared on the interval -1 to 2. So to find the average value of the function, we just need to use that formula that we just learned. So I'm going to write down that my average value should be equal to 1 over my b minus my a, the integral from a to b of f of x dx. So to get the average value of the function, I just have to evaluate what this definite integral is. So in the front, I have 1 over 2 minus a -1. So that's 1 over 2 plus 1, or 1/3. So I'm going to have a 1/3. And then I need to find the antiderivative of 1 plus x squared. And then I need to evaluate it at 2 and -1 and do my subtraction in between. So what is the antiderivative of 1 plus x squared? Well, the antiderivative of 1 is x. And then for the x squared, we have to do our power rule. Add 1 to the exponent, divide by the new exponent. So I have x plus a 1/3 x to the 3rd. Now I just have to plug in our values. So I have my 1/3 on the outside. When I plug in 2, I get 2 plus 1/3 times 2 to the 3rd. When I plug in the -1, I get -1 plus 1/3 times -1 to the 3rd. And so now I just have to simplify this and just be careful with my negative signs. So I have a 1/3 on the very outside. And then inside, I have a 2 plus 8/3 minus a -1, so that's +1. And then -1 to the 3rd is -1, so I have minus -1/3. So that's plus 1/3. So I have 2 plus 1 is 3, 8/3 plus 1/3 is 9/3, which is also 3. So this is 1/3 times 3 plus 3, which is 6. So I get an average value of 2 for that function on that interval. So if you're asked to find the average value of a function on an interval, you can find it by just doing this formula, the 1 over b minus a, integral of f of x dx from a to b. All right, so now we need to learn how to do some more complicated definite integral problems using substitution. Substitution for definite integrals is very similar to substitution for indefinite integrals. There's just a couple things that different people do different ways, so I'm going to show you all the different ways I can think of that people do these problems. Find the way that works best for you. So first, let's write down exactly how to do substitution with definite integrals. If g prime is continuous on the interval AB, and f is continuous on the range of u equals g of x, then we have the definite integral from a to b of f of g of x times g prime of x dx is equal to the integral from g of a to g of b of f of u du. So what this is saying is we can do our u substitution like we already learned with indefinite integrals. We can do the same thing with definite integrals, but notice the bounds of integration have changed. So instead of being a to b, I get g of a to g of b, which is exactly what I get when I plug my original bounds into my substitution u. So we're going to do some examples of this definite integration using substitution. Our first example, we're going to have the integral from 1 to 2 of 1 over 3 minus 5x squared dx. So notice I have a bunch of stuff inside those parentheses. Remember from when we did u substitution with indefinite integrals, I suggested that you use u equals the stuff in the parentheses anytime you have parentheses in a problem. So that's where I'm going to start. We're going to let u equal 3 minus 5x. And then remember we find du by taking the derivative of our u and multiplying by dx. And the last time that we did substitution, we solved for our du a lot, or solved for our dx a lot of the time. So I get du divided by -5 is equal to dx. Now's the part where things are a little bit different since it's a definite integral. If I rewrite this problem, so now I have u's instead of x's in my integral, I can't have bounds of 1 and 2 anymore. 1 and 2 were x values. I need to find the u values that match those. So I take one of my bounds. If x equals 1, then my u is going to equal 3 minus 5 times 1, which is -2. And if my x is equal to 2, then my u equals 3 minus 5 times 2, which is -7. So now I can rewrite this problem so it's all in terms of u instead of x. To do this, rewrite your bounds of integration. I now have u going from -2 to -7. I had 1 over my u squared, and then my dx was equal to du over -5. So now everything has all u's in it. To finish solving this, I'm going to pull my constant out in the front. And I'm going to rewrite that as a u to the -2 power. And now I'm ready to find my antiderivative. So my antiderivative of this u to the negative 2 would be a u to the negative 1, and then I divide by that negative 1. When I divide by the negative 1, it's going to change this negative 1/5 on the outside to a positive 1/5. And now I just have to plug in my values and simplify. So I get a 1/5 negative 7 to the negative 1 minus a 1/5 negative 2 to the negative 1. And we can simplify that a little bit. Remember, a negative 1 power, we just get to flip this to the denominator. So I'm going to have a 1/5 times a 1 over negative 7, and then minus a 1/5 times a 1 over negative 2. So this is a negative 1 over 35 plus 1 over 10. And if I get a common denominator on that, I will get my final answer. So we're going to get, well, I guess I'm just going to have to use 350 as my common denominator. So that is silly. I don't need to use 350. I can use 70. So I'm going to have a negative 2 over 70 plus 7 over 70, which is 5 over 70. And then I can just try to simplify my answer. 5 over 70 is the same thing as 1 over 14, and that's the answer to my problem. So with definite integration and u substitution, nothing's really that different. It's just one of our options is changing our bounds of integration. That's plugging those x values into your u and changing that value on those bounds. That's actually the way I like to do my u substitution for definite integrals, but there are other ways to do this. And I'm going to show you another couple of ways to do this on the next two examples. So our next example, let's do the definite integral from 1/2 to 1 of cosine of x to the negative 2 over x cubed dx. So the first thing I notice is I really do not like that x to the negative 2 inside my cosine. I'm going to try to hide that inside of my substitution. So let's let u equal x to the negative 2. Well, then my du is the derivative of that. That's a negative 2 x to the negative 3 dx. And so my dx is equal to a x to the 3rd times du divided by negative 2. All right, so last example that we did, we then changed our bounds of integration. This time I'm not going to. I'm going to leave my bounds alone, but I'm going to leave a little note to myself that, hey, those values are x values and not u values. So be very careful to not plug them in for your u. So if I rewrite this problem without changing my bounds of integration, I'm going to have an integral from x equals 1/2 to x equals 1. Of my cosine of u. I had an x to the 3rd in the denominator, and then my dx was x to the 3rd du over negative 2. And notice those x to the 3rds are going to cancel out the way they're supposed to. Remember, when you're doing substitution, you want everything inside of the integral to become things involving u instead of x. So I'm going to pull my constant in the front. I have a negative 1/2 integral from x equals 1/2 to x equals 1 of cosine u du. The antiderivative of cosine is sine, so I have a negative 1/2 sine of u, and then I would be plugging in x equals 1 and x equals 1/2. But notice, this is why I write a note to myself that those are x values and not u, because I can't just take this 1 and 1/2 and plug it in there in the sign, because u is inside of my sign and not x. So now is where I back substitute. I plug that u back in, so my problem has x's again. So I have my negative 1/2 sine of x to the negative 2. And I'm going to plug in 1 and 1/2 for my x values. So I get negative 1/2 sine of 1 to the negative 2 minus negative 1/2 sine of 1/2 to the negative 2. And I can't really simplify this too much because we don't know what sign of those values are, but we can at least write this as a negative 1/2 sine of 1 and a positive 1/2 sine of 4 by just simplifying those exponents inside. And this is my final answer. So think about the two examples we just did. The first example, I changed my bounds of integration so that my bounds were u values instead of x values. When you change your bounds of integration, as soon as you find the antiderivative, you can plug those new bounds directly in for u. The second way that I did not change my bounds of integration, and instead I back substituted and plugged that u value back in before I plugged in my bounds of integration. Either way is fine, and you get to the right answer either way. I personally like changing my bounds because I would rather do the work at the beginning rather than at the end, but really they end up being about the same amount of work either way. So you just need to find your personal preference. Let me do another one, and this time I'm going to change my bounds of integration again. So let's evaluate the integral from 1 to 2 of x square root of x minus 1 dx. This problem is actually going to be a little bit tricky, but it's not going to be too terrible. So what we're going to do first is pick out our u. And since I have stuff underneath that square root other than just an x, that's going to be my u value. Let's let u equal x minus 1. Well, then du would be equal to just dx. Let's take a look at this for a second, because this looks a little funny. Remember, when you're doing u substitution, you're going to want everything to become a u instead of an x. If I were to rewrite my integral right now, I would have an x and a square root of u, and my dx is equal to du. And nothing canceled that x out. So did we screw up somewhere? Did something go wrong? No. They're just trying to trick us and making this problem a little more difficult. Take a look at our substitution here. U is equal to x minus 1. I can solve that to get u plus 1 is equal to x. That means when I rewrite my integral, I can replace that x with u plus 1, and then I have my square root of u du. And I will have everything in terms of u, so we're good to go. All right, so that's a little more complicated, but it's not too bad. Now let's go ahead and change our bounds of integration. When x is equal to 1, I get u is equal to 1 minus 1, which is 0. And if x is equal to 2, my u is equal to 2 minus 1, which is 1. So now let me rewrite my integral using all of this information. Instead of my bounds of integration being 1 to 2, they're going to be from 0 to 1. I had my x, which was u plus 1, my square root of u, and my dx becomes du. So now I have everything in terms of u, and we're ready to integrate. Remember that square root of u is the same thing as u to the 1/2 power. So I'm going to write it as a 1/2 power, and then I'm going to distribute before I integrate. So if I distribute that u to the 1/2, I have an integral from 0 to 1, u to the 3/2 plus u to the 1/2 du. And now I'm ready to find my antiderivative. So to find the antiderivative, that's all just the power rule. Add 1 to the exponent, divide by the new exponent. So when I add 1 to the exponent for the u to the 3/2, I get u to the 5/2. Dividing by 5/2 is the same as multiplying by 2/5. For u to the 1/2, I add 1 to the exponent to get 3/2. Divide by the new exponent is multiplying by 2/3. And then I'm going to plug in my values, 1 and 0. So when I plug in the 1, I get this. And then when I plug in the 0, I get this. And now it's just a matter of simplification. Well, luckily, 1 to any power is going to be 1, and 0 to any power is going to be 0. So this ends up being fairly simple to simplify. I'm just going to get 2/5 plus 2/3, which if I get a common denominator of 15, I'm going to get 6 over 15 plus 10 over 15, which is equal to 16 over 15 as my final answer. Now, if we had wanted to, I could have skipped changing my bounds of integration, and then we could have found the antiderivative, plugged the u back in, and then plug in my original bounds instead of my new bounds. And I would still get 16 over 15. Either way works. All right, so now we're ready to learn how to do some complicated, well, not really complicated, just slightly more complicated fundamental theorem of calculus problems. Remember that the fundamental theorem of calculus says that if g of x was equal to the integral from a to x of f of t dt, then we have that the derivative of g is equal to my f with x plugged into it. That was a super nice theorem that we learned in an earlier video. Well, now we're going to learn how do we deal with this if I happen to have something other than just an x as one of my bounds of integration. And it's all going to involve kind of doing substitution, or you can think of it as a chain rule. So if g of x is equal to an integral from some number to some function of x of f of t dt, then my g prime of x is going to be equal to f with that top bound plugged into it times the derivative of that function. So that's doing a chain rule. We're kind of like doing a substitution. So let's do a couple examples doing this. First example, let's do find the derivative with respect to x of the integral from 1 to x to the 4th of secant of t dt. So I'm going to use that fundamental theorem of calculus, and notice that I have this x to the fourth up here instead of just an x. So we're going to let u equal x to the fourth. So I'm trying to find the derivative of an integral from 1 to u of secant of t dt. Using my chain rule, which we already described, I'm going to get the derivative with respect to u, integral from 1 to u, secant t dt, times the derivative of u with respect to x. That's just using my chain rule. So now all I have to do is apply my fundamental theorem of calculus. So this derivative is going to be equal to my function secant, with that u plugged into it, times the derivative of u with respect to x. Now I just have to plug my u back in. So I get secant of x to the fourth times the derivative of x to the fourth, 4x to the third. So this was showing every single step, but notice that to get to the final answer, all I had to do was plug that function of x in to my secant and then multiply by the derivative of that. Let's do one more sort of complicated example. Find f prime of x if f of x is equal to an integral from 2x to 3x of u squared minus 1 over u squared plus 1 du. So what makes this problem different from the one we just did? I'm not just having an integral from a number to a function of x. I have a function of x on both the top and the bottom of this particular problem. Well, what can I do? Well, I can rewrite this as two different integrals using those bounds of integration and a number. And choose a number that's easy to work with. I would suggest 0. So if I rewrite this, I have f of x is equal to an integral from 2x to 0, u squared minus 1 over u squared plus 1 du, plus the integral from 0 to 3x of that same thing. That was just using some of our properties of definite integrals. Now, I had another property of definite integrals that said if I flip the order of integration, it makes the integral negative. So I'm going to flip this guy upside down so it looks like my fundamental theorem of calculus, so I can apply that theorem a little easier. So when I flip this guy upside down, it's going to make it negative. So I get f of x is equal to negative integral from 0 to 2x, u squared minus 1 over u squared plus 1 du, plus the integral from 0 to 3x, u squared minus 1 over u squared plus 1 du. And now I'm ready to use my fundamental theorem of calculus with a chain rule. Remember, all it said that we have to do to take this derivative is you plug in this top bound of integration for all of the variables, and then you multiply by the derivative of the function that's up at the top of your bounds of integration. So, using that more complicated fundamental theorem of calculus, I get f prime is equal to negative, plug in the 2x for all of my u's, and multiply by the derivative of 2x, which is 2. And then I do the same thing with the next integral. I plug in that 3x for all of the u's, and multiply by the derivative of 3x, which is 3. And I wouldn't simplify this too much. I would just do a little bit of simplification. I know that a 2x squared is the same thing as 4x squared. So I'm going to write this, move the 2 in the front. I have 4x squared minus 1 over 4x squared plus 1. And then I have plus 3. And this guy, that 3x in parentheses squared, is 9x squared minus 1 over 9x squared plus 1. And I would just leave my final answer right there. I mean, if you really wanted to, I guess you could try to simplify it more. I just personally would not bother. I would leave it right there. All right, so in this video, we learned the average value of a function, 1 over b minus a, integral from a to b, f of x dx. We learned how to do substitution with definite integrals, either changing our bounds of integration or back substituting before we plug the original bounds in. And we learned how to do a slightly more complicated fundamental theorem of calculus using our chain rule. So let me know if you have any questions. You can drop them down below. If you're a current student, you can come to office hours or email your questions. So I would suggest you just get lots of practice in on this substitution. The more you do, the easier it gets. And that's all I have for you today.